Here we have a GPSS. We can run it, and it looks like decade ago application. Actually, it's quite old style, but the syntaxes of the GPSS and the usage of GPSS is a very usable even nowadays. Well, what we'll be doing with this application? Literally, you can find out even samples of projects, by the way. So when you will install the GPSS, you can find out samples in C drive, program files. In 64-bit computers, you have to look for program files 86, which is the program files for 32-bit computers. If you're using 32-bit computer, it will be just the program files. Then it's gonna be minute man software, and then GPSS, student version, and then samples. And here you can find out tons of samples. Actually, most of the samples are quite nicely written. And let's maybe take a look on the very first one, like the sample one, just to find out what is it, what is this app, how we can use it. Well, something like this. So here, actually, we will be dealing with the textual comments. Maybe some of you guys already, tried might be um, um, maybe programming or something or whatever. Or, for example, you remember when we were using a power sim, we were trying to, you know, write equations. So here we can write equations as well, and here we can write comments which can be executed, which can be run. The only question is always, what are those comments? What do we write in addition to the comments? What all this means? And how we can run a simulation? How is it possible to get any of the results? Okay, so um, let's maybe start with the following. So the writing form here contains comments. For example, those are texts which can be written on the right side of the semicolon, like we have them here written, and things or the text which is written on the right side of the star. So both cases are comments, and comments doesn't affect the model itself. It doesn't affect, a simulation. If you remember, we even wrote and copied a text into the PowerSim model. So actually, it's something quite similar to this one. So we can even erase this huge text, and it wouldn't make any of impacts. Well, I think it's quite simple. Um, yeah. Yeah, that's the idea. I suppose it's pretty understandable. Well, guys, please wait a bit. I will try to maybe open the chat on the mobile, so I wouldn't need to switch between screens. Hmm. Okay, there was some side effect related to, doubled microphone appearing in the room. So let me open the chat so I would see it. Could you please write something in the chat so I would see the chat is working? Okay, yes, thank you, Zero. I see the dot you wrote. Yes, thank you. I just want mm, to make the session, the recording without any interruptions, looking for the chat. Okay, so what do we have here? Well, this text we have here can be imagined as an instruction set. Well, when we were working with the power sim, how did we set up the simulation, guys? We set up the simulation specifying the time, the starting time of simulation, ending time of simulation. Then we specify the time step. Put a plus in the chat if you remember this case. Okay, I see no updates in the chat. But I really hope you remember. In the Power Sim, we set up the beginning of simulation, we set up the end moment of simulation, and we have the time steps by which we are hopping between time moments. Okay, so that's the idea, and that idea was for the Power Sim. Here, what we do, we can work in the similar manner, and we can work in a bit different manner. Here we cannot set up the beginning time and ending time. The beginning time moment will always be a zero, and ending time moment depends on how do we write the codes, how do we write the comments, and so on and so on. For example, this code which we have here, it can be expressed as a scenario. Well, actually, whichever simulation equations, they are scenario of a simulation. Here it's the same. We have a scenario, and the scenario is gonna be executed. For example, you can imagine the execution of scenario in the similar manner as you read the book. So you read, for example, one word, you read another word, you read the third word, then you go to the next line and you read another one, and so on and so on. So this text, again, can be expressed as a scenario. And there should be something that runs the scenario, something that executes this. For example, when you write equation in the Excel, the opened Excel on your computer runs the Excel equation. In the same time, on your computer there could be some few Excels opened, right? And one will run some long-term equation, another will run some long-term equation. So both of your Excels will work simultaneously. Same is possible even here. So we can have one scenario, one set of equations, one set of comments, and it can be run in the parallel multiple times. And we have an executor which runs the scenario. Um, and we can provide timings when additional scenario executor appears in the system. Well, the analogy from the life can be related to movies and to the actors. So I suppose you quite frequently, I suppose, watch movies, right? Is it so? Yes. Okay. So for sure, I'm starting this description how to say from the Adam and Eve, but it's the best way how to describe this. So literally, this scenario needs to be executed, and it's the same like in movies. So they're actors, and maybe well, um, you can correct me, but in the movies, for example, if you have some action being filmed, right? they're actors who are doing something, right? So literally here we will have the same story. We will have several actors which will run the scenario we have. For example, there could be a dialogue, there could be, manipulations with some objects, maybe communication with other actors, and so on and so on. Literally here we can specify something like a scene on which actors appear, and each actor receives a full set of these comments. So even if this file would be super long, each of the actors appearing in our simulation on our simulation scene will receive the full code we have. And there could be the question, well, okay, if the actor executes the scenario, runs the scenario, so what happens in the end? In the end, when all of the actors they finished working with the scenario and they reach to the specific code that ends the scenario, they disappear from the scene. The same like it happens in movies. And actually, the simulation here in the GPSS can last not till some specific time moment will be reached. Also, we can do that. But the second way is to say, well, we are running a scenario, we are running the simulation until, let's say, 5 actors will leave the scene. So, yeah, so that's the most general way of running these equations, running these operations, without mentioning what those operations are and how we should understand them. The next thing is that here each row contains for sure contains the comment and contains the operation. So here operations are written in the Polish notation. Guys, do you know Polish notation? Do you know what is it? Okay, so the Polish notation is being created by one Polish philosopher literally centuries ago. And the Polish notation is being used in the IT during the beginning of the computers as we know them. So, for example, an equation a plus b. Okay, a good equation, but the machine, the computer, will need to know the operation, and only then will have to receive operands. In other words, the numbers or maybe unknowns, which will be affected by the operation. So, for example, a plus b. In the Polish notation form, it's writable into a into plus ab. So firstly the operation happens and then operands. And it's known for the machine and for us as readers that we have the plus, and plus works on two operands, on two values. And then we receive these two values. That's the Polish notation. And Polish notation is being used in the GPSS. So without any specification about what has been meant by each of the comments is being prepared in the following way. Firstly, we have the name of the comment, and only then we have several parameters we can give for this comment. Does it make a sense? So, for example, we have the comment generate. And running the comment generate, we're given two numbers for the comment generate without any specifications what the generate is. For example, depart barber, right? Okay, we have the comment depart, and the barber is the argument which has been given to the comment depart. And moreover, if we will return to the analogy with the actors or the executors of scenario, the executors of operations, so we have an executor, the actor, which which runs the depart command related to the barber object. That's how these commands they have to be understood. Does it make a sense, guys? Is it understandable how all these codes are being written? Like what is the principle of writing them? Mhm. Okay, great. So the next thing is that we have to deep dive into an understanding of what each element means here. And before I will describe, I will probably rename two values. This one. So um, in this code we have the actor, or as by GPSS syntaxes it's called as the transact or the executor. So it appears within the command generate. Here the story is very simple. Let me maybe describe you firstly the essence of this task, and then we will go in details about what each command means. So we have the barber shop, and a new customer arrive in the time between 200 time units till 400 time units after the previous customer. Once they arrive to the barber shop, they stand in the waiting line, and every of the customers they wait until it will be possible for the barber to mm, to invite them to take the barber's seat to be served. So to be serviced, better to say. And once they've been invited, they leave the line of they leave the waiting line. So they're not waiting anymore to receive the service. So when the transact leaves is being invited by the barber, and the customer left the waiting line, there is the time being spent for the service. After that, the barber doesn't work with that customer anymore, and the customer goes out from the barber shop and being registered as another customer went out from the barber shop. So does is the narrative clear for us, guys? Great. Well, I think this is pretty basic and daily routine, right? But let's take a look in details, and let's try to understand how each of these commands working. So the generate always says us um, how transacts appear in the system. So every operation we have here written will be run, will be executed, will be operated by the transact or by the actor, if you like to say it that way. So so literally we have transact appearing by the generate code, and then each of the transacts execute or tries to execute each of the commands they can, or going from top to the bottom in the same order as I highlighted the lines of the code. So what happens when they cannot execute the line? For example, one of customers was invited to take a seat on the barber's chair. Okay, that's great. All is good. But as we know, if one customer is receiving service from the barber, right? So another one cannot be invited. I think you will agree. So that means that if only another transact mm, cannot take, well, how as I call this, cannot take the slot of the barber. So the transact is just waiting till the time moment when the operation will be possible to be executed. Well, that's the idea. So here we have to deep dive maybe in the understanding of what kind of objects, what kind of elements we can work within a GPSS. So the waiting line. So here I have to ensure that before using the object, we don't have to declare that. In many of programming languages and in the PowerSim as well, we couldn't use the name, or we couldn't use the variable without defining it. Here it's a bit different. We can use them, but if in the memory there was no such variable, no such object, then it will be created automatically. So, for example, the line. Oh, and by the way, different types of objects, they can be named by the same name. That's why code of the GPSS can sometimes be confusing. So that's why I renamed the barber waiting line to the line, so it would be more clear for us. So the line, so according to the line, to the waiting line, the transact can have only two operations: the queue and depart. I think the separations already means the essence of this. So the queue literally is being executed as transacts. Transact takes the place in the line. So literally it's been attached to the line. And depart means that transact leaves the line. And operations queue and depart can be used only to the lines. That's it. Only to the so-called queues. That's it. Okay. Then we have the barber. For the barber, we can use only two operations: seize and release. I think by the commands names, it's understandable what do they mean. To make the story, to make the long story short, guys, I can say, for example, how I imagine all this. I imagine all this in a way that transact is something that takes the place, and we have such objects as one slot or multi-slot objects like barber, which can work simultaneously with one transact only. So as I try to imagine this all time, as in a way, is that barber is like the one slot machine, and that slot can be empty or can be filled with the transact. Maybe it will be easy even for you guys to imagine this in a such way. So that means that barber, or as it's called in the GPSS syntax, is a facility. So the facility can work only. So we can have um, only one transact attached to the facility at once. I mean simultaneously. So once transact is attached to the facility, another transact cannot be attached to the facility as well, because because there's no free place, or there are no free slots for another transact. That's the idea. And by release, the transact makes the facility free, or facility slot becomes free of the transact. So that's the way how you can understand this. Um, so in other words, every transact stands in the line. Only the transact which reached the case when the barber slot is free fills that slot with itself, or is being attached to the facility in GPSS. um, sentences, how to say, then leaves the line, then the time is being passed for that transact. So here it will be like 400 time units in average, and plus minus 200. So the first parameter for the timing for generate and advance means the average time, and the second means the time dispersion. So as for the generate, the time means 300 plus minus 100 time units um, after the previous transact went into the system. The advance is just how to say phrases the transact for 400 time units plus minus 200, and then afterwards the facility becomes free of the transact, and transact is being taken out from the system, registering that one transact went out. Guys, is my description about the code and the way it runs was understandable for you? What would you say? Mm-hmm. Sort of, but yes. Okay, great. Because I try to give you as many analogies as I can give you. So literally, you can imagine that there are actors who are playing visiting the barber, right? So what happens? So the first one appears in the time period 300 seconds plus minus 100. Then after the first appear, then again 300 time units happens or seconds happens plus minus 100. Then the second appears, and both of them are waiting in the line. And only when the barber will be free, barber will invite that actor to take a barber's seat and to receive the service. Literally, you can imagine that this is the scenario of the movie, and you have actors appearing through the generate, and they leave the scene using the command terminate. Maybe it will be easier to understand this. But every of the actors they receive the full scenario. And if we have in the scenario some branches, some I would say conclusions or conditions, how they have to work, what they have to do, they then they can go even outside the generate terminate block, but that happens on the reason. So at this point we have this code. So how can we run it? We can go for comment, and we can create the simulation. So if we don't see any error messages and we have the text that model is ready, we can run it by the command start. And here for the start, we have to mention amount of transacts we will wait to be out from the system, and until that moment, a simulation will be running. For example, start 10 means that we're making simulation till the case or till the situation when the customer number 10 will leave the system. So let's run it, clicking OK. So what do we have? So we have a small report. So here we have beginning time of the simulation. Here we have the ending time of the simulation. That means that, well, literally such many time units went until the customer number 10 went out from the barber shop. Well, our assumption would be that this number could be, written in seconds. Well, that slightly depends on our assumption. What is the time unit? It's up to us. And for example, if those are seconds, so we can take this value and we can, calculate what is it in minutes, for example. Okay, that's gonna be 77 minutes. Okay, good. Then we have names of the objects in the system. Here we can have even variables when we create them. And as for variables, we will see the actual values. But as for objects, they will be their identifiers in the system. So we're not really interested in those identifiers. So for now, we can just leave this part of the report. Then we have all of the comments mentioned. And here we have a small report about how many transacts executed those operations. So generate 15. That means that 15 transacts were generated. So 15 customers appeared in this system, in this simulation. So since 11 means that only 11 customers were asked or were invited by Barber to receive the service. 10 left the waiting line. 10 were waiting until the service is being done. 10 customers left the barber, and 10 customers went out from the system. So the current count. So on the moment of stopping the simulation, literally we see how many transacts right now are in the process of execution the command, or you can call it as how many transacts stack in which equation or which command executions. For example, here we have 4, and we can imagine this as 4 clients are still waiting into the line. So the last command for them was running or the taking place into the line. One of them, or one of those 4 plus 1 customers was invited to no, one of those one of those 5 actually was invited to the barber's seat. So here we had 4 left. One has been invited. So literally we have like 5 customers in the barber shop when simulation stopped. And the last column is just amount of tries to reach to the line of the code or to execute the line of the code again for the transact. Okay, so the next thing, the facility report. So here we have amount of transacts which overtook the slot of the facility. Then we have the overall utilization of the facility. So it means, in other words, in the percentage, what percentage of the time facility had the transact connected to the facility. In other words, what time the barber in the percentage was taken making the service. And we can say the time for the barber making the service was 92% of the overall time. Then we have the average time. So that's the average time for one transact to receive the service in the average. The next one, if on the simulation stopping moment, the facility has connection to the transact, or if the slot of the facility is taken by the transact on the moment when simulation being stopped. And all the rest is not very interesting. Nextly, we have the small report about the line. So a maximal amount of transacts simultaneously appearing in the line, amount of transacts on the moment when simulation being stopped, amount of transacts appeared in the line, average amount of transacts for one time unit, average time for the transact to be in this line. Well, and the rest is again not very interesting. And this part is not interesting as well, at least for now. So that's the statistical data we can receive running the simulation. So guys, is it clear at least approximately what we can get from the report? Okay, great. So let's make the step forward. Let's close the report. Let's close the creation of the simulation. So yeah, so here we have a very simplified way of the comment. So what can be interesting in addition here? Um, maybe I can, maybe I can open materials. So to make this talk a bit more structured, because if you understood the main principle at this point, then it will be quite understandable related to all of the rest. So let's maybe take this one. And I will probably, oh, you know what? I can probably describe you the code which we have right here. So let's maybe open the barber GPS. So it's not the sample one. This solution is a bit broader. So what do we have right here? Right here we have a bit of the extension of the previous code of the previous model, and here we have the following idea. So before the operation, we have the name of the line. Literally, we can use names of the lines as destinations to which we can transfer the transact. So we can have the Q table. Well, about the Q table, maybe I will not be describing a lot. Let's maybe take a look on the following. So we have the waiting line called barber. So this barber and this barber is not the same, right? So this barber is the waiting line and this barber is the facility. I think at this point you already understood this. So what else do we have here? We have the same generate. Right now we have just another numbers here. It might be one here means 1 minute. I'm not really sure, but let's imagine it that way. So we have the time with dispersion when the new transact appears in the system, and here we have a very interesting operator. So operation test. Frankenstein is the same as operation if. Nextly, we have comparison operator. And then we have two values which are going to be compared. And if comparison is correct, then we pull the transact to the next line. But if the comparison is not correct, then we pull the transact to the name of the line, which is mentioned as the third parameter. So in other words, that will be forced to leave the system. Idea here is very simple. We have test and then we have LE. This LE means less or equal. I can show you maybe in the presentation if I have it in this one. If I have it in another one, I will show you another one. No, looks like I have to open you the next one. Yes, here. So we write test, then we write comparison operator, and then we have ABC arguments. So LE is less or equal. L means less. Um, G means greater. GE means greater or equal. E means equal. NE means not equal. Literally, if we have LE, that means A, or the value which stands in the position A is less or equal to B. And again, if only this equation is correct, if only this comparison, or let's call it condition, is correct, then transact goes to the next line. Otherwise, it's being pulled to the line with the name which is written into parameter C. That's the idea of the operator test. So if we will return to the code, here we would have a 1. Okay, Frank is saying numerical value, all is good. Finish as well, the name of the line, which is written here, so all is good. So what is Q $ barber? That could be the question. And here we have the Q $, which means that we are affecting some of the values. And here Q means the len or amount of transacts in the line. That means that on the right side of Q $, we have to mention the line's name. Literally here barber is the same like it's written here and as it's written here. That's the line. So idea here is the following. Transact appears in the system, or if you like, the customer appears in the system. So if amount of people in the line or amount of transacts in the line is less or equal to 1, then transact stays. Otherwise, transact leaves. So it goes to the code line with the name finish, so literally here, and it executes the operation terminate. So it goes out from the system. That's the idea. So next, we have here a very unusual operation, and this is maybe one of probably complicated things related to GPSS. Here we have variable custom, which appears in two different manners in this system, in this model. So here, these two lines can be written in the form as custom is equal to custom plus 1. That's the overall idea by these two code lines. So the first part, the summation, is being run here. Literally, that means that into the custom, we add the value 1. So it's custom plus 1. And that will be the result of a so-called short-term variable called custom. Actually, here for the save value, we have the syntaxes. Save value, then a first operator or a destination in which value is being saved. Then potentially we can put a plus or minus or nothing. And then the second argument is another numerical value. So when here we have nothing, that means that custom becomes 1. If only here it's minus, then it means the custom is custom minus 1. When it's plus, it means the custom is equal to custom plus 1. And it's been saved into the short-term memory. That has to be remembered, the short-term memory. Then, by the assigned, we save the value from the short-term memory. We receive numerical value from the short-term variable custom, and we save that to the long-term variable. That's how it has to be understood. And all the rest here is the same like we just took a look at. Is this example clear for you guys? What would you say? All right, maybe let's take a look on the report. So we are creating simulation, and we run a simulation until 10 customers will leave the barber shop. Okay, so here we have the report. So we have begin time of the simulation, we have the finish time of the simulation, we have some objects with their values. Well, those values are just identifiers. Again, we have amount of transacts which reach to the code lines. Okay. Um, and we have amount of transacts stuck on the moment of interrupting the simulation as well. So literally, what do we see by this report? Well, we see that on the moment when customer number 10 went out from the barber shop, uh, we we had like 9 customers being being reached till waiting. That's overlay. And on the moment of simulation stopping, only 2 were waiting in the line. Because again, so if the line is less or equal to 1, then customer stays. So it means that overlay, then we have maximum like 2 customers in the waiting line. I think that's understandable. And all the rest is just facilities and quiz report, which is frankly saying understandable. The only thing we have to take a look how many of the customers really had the service, or how many of them stayed, better to say, um, based on the amount of clients in the waiting line is 9. So when the value or when the variable is being just used and it's not being assigned previously, that value becomes a 0. So that means each time the customer leaves, the customer stays, based on this comparison between the waiting line and amount of people in the waiting line assumed to be fine, then we just increase the cost num. So it means 9 of the customers stayed into the barbershop. That's the idea. Do we have any questions related to this example? Okay, no questions. Okay, that's great. All right, so I suppose then you could, you have to always try to make implementations. And for example, I would like to ask you maybe to think about the following task. How it would be possible to implement this. So it's known that there is the football stadium, and it's known that people will go to the football stadium. So a new guy appears, going to the stadium, uh, in the time period between a 0 and 14 seconds, from the time when previous one came. So all of those guys, they're standing in the line, and they're waiting their turn to be checked by a so-called face control. So the face control takes, in the average 5 seconds plus minus 3 seconds, and it's known that we have to find out the time in these conditions to make sure that 300 people will go inside the stadium. So we have to find out this time. For 300 people would be already on the stadium. So the question for you guys, may I ask you at least to try to code such solution? Or maybe you would like to make this one together. Yeah, sure, we can make this together, yes. Maybe I will show you firstly the implementation, which includes additional knowledge. So here we have this implementation, but we have even additional variables to be just separately specified, and then we could use their values. So the variable is in use, and variable is range. So in use is equal to 5, range is equal to 3. And as you can see, we can use them instead of numbers. Okay, all this is good, but let's create a simulation. So what I will be doing, guys, I will create the new model. That's gonna be the first thing. So I press on the new, and we choose the model to be created. Okay. And now we have to mention all of those actions which we read from the task definition. So we will have generate. And what does it mean that the new guy appears in the time period between 0 and 14 seconds? And that means 7 plus minus 7. Okay, for sure, once the guy went inside, right, the line, he has to take the line. Okay, let's say the guy takes the line, and the guy waits until the face control will reach to that guy. In other words, he waits while the face control will be free for him. So um, we have the command says face control. Okay, so as we understand, the face control operation is being run or executed only when there was the opportunity for that. If the face control is busy with other people or with other transacts, then this execution will not happen for the current transact that runs this code. Okay, so once the face control started to take a look on that guy automatically is out from the waiting line. And actually, the face control takes the time, so it's 5 seconds in the average plus minus 3. Okay, so once this is done, so phase control can allow the guy to go to the stadium, and by that the phase control is not operating with the transact or with that guy anymore. So literally we are running operation release phase control, and actually that's it. We have terminate and we have won. So if we would like to run the simulation without specifying until how many transacts went out from the system we would like to run the simulation for, we can already write somewhere in the end of the code, start, and then amount of transacts we're waiting to be out from the system and to be registered, to have the registered out from the system. Okay, and now we can run it. So you see, in average, it takes like 2,134 seconds. For sure, we can even convert this to 2 minutes. So it's gonna be divided by 60. So it's gonna be a bit more than the half an hour, a half of hour. That's the idea. And surely we have the overall utilization of the phase control. So literally it's 69% of the time when phase control was looking on people deciding to let them go into stadium or not to go to the stadium. That's the idea. So how do you find the solution? Does it look easy? What would you say? Yes, it's all right, exactly. Because the only thing we have to remember, well, what type of comments we are making and what are we doing this for. That's the main that's the main thing actually. All right, so let's maybe take a look on the next examples, or maybe a bit more interesting examples. So between the codes or between the comments, we can have the such one, the comment called transfer. The transfer command contains four parameters A, B, C, and D. So the argument A that literally gives us the opportunity um, to have a condition to pull the transact in one of those names of the lines which can be placed in B, C, and D parameters. The parameter number A, it can be free, so it can be empty. That means that by default, or without any condition, we're pulling the transact into the code line B. Well, that code line which is written into the parameter B. Okay, when we have both, or let's say if we have some value between 0 and 1, that will mean that by that percentage of the chance, we will pull transact to the next line. In all of the other cases, for example, this one, well, here if we have filled B and C, that will mean that in 37%, the transact will go to the line B. In all of the rest cases, it will go to the line C. If you have only B mentioned, or if you don't have the B mentioned, that will mean that we're considering the next line. So if it's empty, it means the next line. If it's not empty, it means that line which name you wrote in the parameter. So both literally compares B and firstly try to pull the transact into the line B. If the operation on the line B is executable, then it's fine. If it's not executable, then it tries to pull it to the line C. And again checks if the operation in the line C is executable for the transact. If it is, then it's been left there. If it's not, then the story is being repeated, starting with the code line written in the parameter B. If you have a parameter equal to all, that means that the same try will be used for all of the three names of the code lines. And all of the rest cases like peak, function, or the parameteristical block, and other cases, it will not be interesting for us. So that's how the transfer works. There is another interesting operation called gate. Operation gate actually is something similar to if. The only in if or if the test compares the values, then here we compare the state of facility or a storage. Storage is just the multi-slot facility. So for the facilities or the one slot instances, we can have only two possible cases: when the slot of facility is being occupied by transact or is not occupied. Only two states like taken or free. And if only comparison is correct, so for example, we have facility A, and we, for example, have U as the comparison operator. So literally, if A is occupied, if A slot is taken, then we pull transact to the next code line. Otherwise, we pull that to the line with the name which is written in parameter B. That's the idea. So how this is useful and how this is usable. So let's suppose we have the following task. So the phone lines. So there's a telephone line through which the call occur every from 5 to 15 seconds. If the line is busy, so it means occupied by some other call, then the phone should wait between 4 and 6 seconds and should try to connect again. If the call can take place, then the talk itself lasts between 10 and 20 seconds. After that, so the phone call is being interrupted, and the phone call is being disconnected from the line. So again, literally, that's the example from life, right? I suppose you will agree with this. Let's take a look on the solution. So we have the new call appearing in the system in average 10 seconds plus minus 5. Okay, Frank is saying all this is good. Then every call stands in the waiting line. And then we have gate U and line. That means if line is not occupied, so if the facility line is not being occupied by any of the transacts, then we pull the transact to execute the next line and to overtake the line. Otherwise, if line is occupied, then the transact is being pulled to the wait block. Here we have the name of the line wait block. And here we have the freeze time for the transact. So 5 seconds plus minus 1 second. And then without any of condition, the transact is being pulled to once more name of the line. And here again, we check the state of the line. So if line is empty by any of the transacts, then a transact takes the line, goes out from the waiting line, takes the call time between 10 and 20 seconds, and then release the line, so line becomes free, and the phone is being disconnected from the line. And since here we have start 300s, then it means that the simulation will happen until 300 calls will happen. So I suppose there is the similar example in sample folder. Let's take a look on it. So let's try to open sample folder and let's find the telephone or telephone 2 line. Telephone. Oh, this is a bit more advanced one. This is a bit more advanced one. Do we have the just maybe line here or something like that? Okay, we don't have it, but it doesn't matter. So guys, the question is, did you get how this code is being formed? I know it's a lot of things for maybe for one day, but you know, we have to try to move forward. Okay, great. So so here we have just one line which can hold only one call simultaneously. I mean, in the moment. So we can extend this task until the case when we have multi-slot facilities, or as they called in the GPSS, a storage. So all of the storages have to be defined specifically. So we have the name of the storage to make the storage, you know, and the amount of slots of the storage. So in addition, we have to use different comments for the storage to take the transact in its slots. So instead of seize, we use enter, and instead of release, we use leave. And the gate cannot use just occupied or not occupied state. It has to have, for example, is full, so SF, is not full, SNF state, is empty, SE, and is not empty, SNE state. All of those states are being given to you in the presentation, so you can find them. So here they are. So that means that we will have to use different manner of the solution. Oh, sorry, I didn't translate this one. This means the task. So right now we have doubled line, and all the rest of conditions are the same. So what's being created? So here we have the following. We have the lines, and we have two slots of the line. Okay, that's great. So here we use different comparison for the state. It's an SNF. That means is not full. So that means that there is at least one slot which is free. So that means that we can take that slot by the command of well, here it says and release, but I think I just copied that a bit incorrectly, because actually it has to be enter and leave instead of seize and release. Yes, so it's gonna be enter and it's gonna be leave. Um, okay, so what's in addition here we have? Well, all the rest is the same, so we compare if the line can take a new phone call. If it can, then we have the well already known set of actions. If it's not so, then again we are having something like the waiting between another try to connect. As you can see here, for the transfer, we don't have the first argument. That means that it's empty. Well, that's the idea of this. And that's the way how we can use the storages. So guys, is this example clear for us? Mhm. Okay, great, great. Okay, so let's move forward because there are tons of new things, and let's call it other things which we can use. So the general block itself, it contains 7 parameters. In more advanced versions of the GPSS, it has even more of these parameters. But before this, we used only two of such. Those are A and B, so the average time and the time dispersion. Okay, so what else we can set up? We can set up the appearance in the time units for the first transact generated by the generate. We can specify amount of transacts which will appear in the system simultaneously. We have the priority. Next, we have the parameter amount. Well, parameter is just, details about the transact. So parameter types of parameter amounts will not be overlooked during the course because it's a bit more difficult. It's a bit more complicated, better to say. That's the idea. So the next thing, instead of the C's and enter, we can have the command called preempt. Preempt command pulls aside the transact, which takes the slot of the facility or the storage, and it occupies that. And the transact which runs the preempt command occupies that slot. For the prim, there is even another parameter, so-called parameter B, in which we can write the statistical data about the transact which is being left by the facility or the storage. So afterwards, potentially it can return to that transact. For example, where we can see such cases, such examples. Let's suppose we have the task for fixing the TVs. So to fix the TV, we can have different fix types. So there could be a so-called the really bad case when a lot of work is needed. There is a small repair, and there is a so-called general or the ordinary repair. So each of those repairs, they have their average appearance, because the small repair televisions appear more frequently than the awful repair needed, right? And for sure, each of them takes even a different amount of time to make the TV repaired. So all these factors, they have to be taken into account, and literally, we can specify those repair or those televisions as transacts, actually, because we will need to create a simulation for, let's say 8 hours of the work. So how that would be doable? And by the way, you can find out the similar solution into samples. Maybe first I will show you and then we'll return to this presentation. So through the samples, you can look for a TV repair. Here you have it. And here you have almost the same code, a bit different one, but anyways. So, or we can just take a look on this one, because there's no huge difference between my code and this code. So we have priorities. So literally we have priorities of the transacts. So a small repair has the highest priority. And as you can see, for the higher priority transacts, we use preempt instead of cease. Well, why? Because actually during the preempt and during the cease, transacts take a look on, the facility and storage take a look on priorities of transacts. And for example, if we reach the case when literally the facility can take one of transacts and one has the highest or the higher priority, then the highest priority transact will be taken by the facility um, or a storage. In the case when facility or storage is already taken by the transact or its slot is being taken by the transact, then by the command print we compare literally a priority level between the current transact which run the print operation and the transact which already took the slot of the maintenance facility. So if the new transact priority is higher, then that transact priority which is being already occupied the facility slot, then that transact which already occupied the facility will be free from facility slot, and the new transact which executed the print command will take the facility's slot, and that previous which was taken up from the slot will be statistically written into PR variable. But actually here we can mention whatever other variable actually. That's the situation, and it's not shown in this case. But afterwards, we can use the PR to get back to the previous transact, which was forced to be to leave the facility's slot. Literally, the repair guy repairs a TV of the overhaul. Well, let's say totally broken TV, right? So someone brought a TV that needs some maybe 5 minutes of the fix. So the master leaves that huge fixed TV, spends 5 minutes on the new TV, and then go back to that TV which he was working on and which here is the saved in the PR variable. But that has to be created in addition to this code, which we have right here. That's the idea. And actually, you can see that once the fix is being done, those TVs disappear from the system using terminate without a number, because we're not registering that those TVs went out. So what has been really registered? And what has been really registered is the following. So we have appearing of the transact after 490 time units. Literally, that means after 490 minutes, if we assume that one time unit is 1 minute. And then, without any of the problematics, the transact goes out from the system. In other words, words, if we have start 1 for running the simulation, it means that our transact will work only during 480 time units. That's it. So is this example clear for you guys? Okay, great. So yes, so that's how to say another example of the GPSS code. And for sure, guys, we can run all of these models, and we can get all of their reports. But actually, they will be plus minus the same, right? And I suppose we have to look them when we have to make a conclusion of the model. In other words, when we have to look for some data. Okay, so that's the thing. Okay, so we can, I assume, close these files. All right. Well, guys, after a few minutes by the schedule, we have to take the break. But do we need the break? What do you think? So, what are your thoughts about the break? Okay, what's about others? Because as earlier we will continue, as faster we will finish. Okay, then I suppose we can continue, and then we will finish, well, really, really faster. Especially because this is something super, super new for you. Um, and I just don't feel like I have to give you the full set of the data of the info from the very, very beginning. That probably will be too much for the one set of classes. Okay, so we're continuing then. So let's move forward, and let's take a look on another examples, extension in our knowledge about the GPSS. So let's move to the next slide, to the next presentation. So here we have a small reminder about every of the aspects which we took a look at. And maybe let's take a look on some of the cool examples. Okay, here we have still some, reminders about how things are doable and so on. So here we have, give me a second. Okay, so here we have a really cool example, guys. Really cool. Again, all of those examples, they come from the live cases. So here we have the car or machine part inspection. So idea here is the following. So we have the fabrics, and the fabric produces spare parts of the cars or of machines, whatever. So it's known that there is the average time in which a new spare part comes from the conveyor. Okay, that time is known. So each spare part has to be examined and has to be tested and tried before sending the spare part to the customer. So this examination of the spare part takes from 60 minutes to an hour and 20 minutes. So if the spare part is good, if the detail is good, then and it happens in the 15% of the chance. Okay, not really cool, but let's assume we have this percentage of the case of the chance. So then the detail over the spare part is being packed and being sent to the customer. But in other cases, so in the rest 85% of the chance, that spare part has to be fixed. And for the fix, there is a guy who is fixing the spare parts, and that takes from 200 minutes to 400 minutes for making these fixes. So we have two testers and we have one fixer, and we have to simulate the process for several working days. Here I have like 5 working days, but actually there will be like 10 working days used. And here we have this quality control code. So we have appearance of spare parts in the system. They go into the line. They being, oh no, we have one tester, two fixers. So we are testing this spare part. That takes the time. Um, then the fixer just puts aside this spare part, and in the 15% of the chance, when the tester says, well, that spare part is good, then it will be just sent to the customer. So it goes out from the system using the terminate. So otherwise, it's been sent to be fixed line. So the question is, why in this case of the transfer 0.15 we pull the spare part to the common terminate, because the component B or the parameter B is empty. So that means we try to use next line. So the transact goes to the terminate line, and otherwise it goes to the line to be fixed. Well, the story is about fixing the spare part is the following. Well, that spare part reaches another waiting line. Then one of fixers takes the spare part and fixes that for a specific amount of time, which, as you know, is 300 minutes plus minus 100. And then such spare part will be sent for another check. And during that another check, that spare part will go inside the waiting line for spare parts to be tested, and then the story is being continued in the same process as I just described you. So anyways, each of the spare parts will leave the system using the terminate command. So in the parallel to all this, we have such amount of minutes for the simulation. So literally where this comes from. So it's literally 60 minutes by 90 by 90, no, 80 hours. So literally 10 working days. That's why we have 480. No, we have 4,800 time units. When we make an assumption that one time unit is equivalent to the 1 minute. So that's our code. And it might be that we have something similar into the samples. Maybe some factory or something like that. I'm not really sure actually if we have such sample, but okay, it doesn't really matter. Okay, so what would you say about this example? Is this example understandable? Okay, great, great. So then let's move forward, and then we will have the car repair or machine repair. Here we have another story, but again from the life. And here we will be dealing with a generate block a bit differently. So we have 53 machines in the on the factory producing something. It's known that the conveyor of the producing work only with 50 machines, and let's say they all are same. So 50 machines are working on the conveyor, and it's known that there are only three repair guys who can simultaneously repair machines. Simultaneously means that we have three guys, so only three machines can be fixed simultaneously. It's known that there is a specific time during which machines can work without any of the maintenance and repairs. And after that, it's known that in the average, it's known that repair or the maintenance time plus minus the time dispersion for that. So it's smaller when it's maintenance, it's bigger when it's a repair process. So and once the machine is being repaired, it's ready to be placed in the it's ready to be placed into the conveyor to start working. And once it will work again, this assumed time, then again that machine will need the maintenance or a repair service. Well, I suppose you understand that again this task comes from the real life. If it's so, please put the plus in the chat. So how to make this? So looks like we have nothing here appearing periodically in the system. For sure, we have those machines which have to be included into conveyor and they have to work, then being maintenance, then again work and being maintenance, and so on and so on. So how this is doable? And here we have a small example. So, and I think by this example, you will find out that GPSS is really elastic for modeling. So we have three masters or the fix guys who can fix or make the maintenance of the machines. We have 50 slots of the 50 slots on the conveyor. Then we generate at once 53 machines, and since we don't have here the average time, we don't have a time dispersion, we don't have the first appearance time, then all these 53 machines will be just generated at once simulation is being started. And that's it. Then generate block will not produce any of other transacts at all. So they appear in only once. And as you can see, guys, there is no terminate or which would be reached by transacts which are generated by this generate block, because it's not been assumed that way. So once we have them, so literally 50 machines have been placed on the conveyor, and three of them will stuck at this line, trying to run this line, but only when the slot on the conveyor will be empty, only then one of those machines will be placed inside the conveyor. Again, it's the same like given this whole scenario to the actors, right? So literally it's something the same. So then there's the working time once the machine is being placed in the conveyor slot, and then after that time, the machine leaves the conveyor slot because it has to be maintained. So the maintenance is needed, or maybe the repair. So the fixed guy takes the machine, works on that, and leaves that machine. So the repair guy becomes free of that machine. And then that machine is being again waited to be placed into conveyor slot, and the story is being repeated all the time, once and once again. In the parallel of that, we have the timer. So, and the timer literally will work as the stopper for the simulation. So, and simulation will last for 500 time units. So the question for you guys, does it make the sense? Is it understandable how this code works? And is the idea of this code is understandable for you? By the way, if you like, you can always rewrite these codes into GPSS and it will be 100% working. Or if you like, you can take the file. It was this one, if I'm not mistaken. Yes, and we can always run it and we can see the results. And here we have the report about masters or fixing guys, and here we have the report about the average time for the machine being worked within conveyor slots. So as more flexible and as more broad statistics we make, as more information we save during the simulation, as more and interesting data we receive after the simulation being done. Literally, we have tons of things available from these reports. Okay, well, do we have any questions about this solution? So what would you say? Okay, can we continue? Can we go to the next example? Or maybe you're thinking about questions. Okay, great. Okay, great. So let's go for the next examples then. So the car washing. And guys, that will be on you. So you will have to provide your solutions for this. So there's the car washing service, and it's known that the new car arrives every from 15 to 25 minutes. So if there's the washing line, in other words, if all of the uh, parking slots are um, occupied for waiting the car wash, then the car drives away. Otherwise, the car stays and takes the parking slot and waits. So the washing itself takes from 12 till 18 minutes. So you have to make the simulation using a GPSS. for the one working day. So literally 8 hours. That will be fine. So please, guys, try to make this solution and try to send your solutions in the chat because you can do that because literally all of your solutions suggest texts you can copy, you can send. So please try to do this. Okay, I will show you that. I will show you that definition again. Here we have it. So please, guys, try to make this. So how do you think? How many minutes do you need for this? Maybe some 10, maybe 15 minutes? What would you say? Guys, please be more active in the chat because if you're not writing me back, if you're not communicating back, so it's kind of complicated. So how many minutes? Like 10 or maybe 15 minutes? Will it be enough for you? Okay then. So guys, then I will leave you for some 10 or maybe 15 minutes, and after that I will ask for your progress. And once you will have anything, please post your solutions in the chat. And then after that, we will try to take a look on the solution and we will try to discuss one of different ways how this is implementable. Okay, so for now I will switch off the microphone for some from 10 till 15 minutes, and then I will activate this again and I will ask for your progress. Okay, guys, so how's the progress? Or maybe you need some more time. So what is the situation? So, guys, hit a message in the chat about your progress. Okay, you failed the simulation. All right, let it be so. So zero has the same case. Okay, at any case, those are, well, how to say, results as well. Even if you failed, uh, at some point, it's already the result. Okay. Anyways, so let's maybe take a look how this is doable. So please take a look, and this is only one of variations. Well, how you could work on how you could work on the solution. So we make the places, right? So literally the parking lots, yes. And so let's say um, there's only one um, waiting place, right? Like there's only one spot. Okay, so let it be so. So the car appears. Then we use the balls. So literally for the balls, we take the code line on the bottom. I mean the next one, if it's not executable, if we cannot make this, then we pull the transact to the line with the name out. Okay, so it's there. So it will be terminate. Okay, great. So literally, then, if only the car took the place, then it enters the place. When the washer is ready, so it takes the washer. Once the car drives to the washer place, so it leaves uh, the parking place. Then the washing happens, and the washer is being released. So the car moves out, and the washer is free and ready to take another car. And by that, after the washer, so the car drives away. And we are simulating this for literally 8 hours. So when one time unit means 1 minute. That's the idea. So, did you understand how solution works? Okay, great. So as you can see, okay, this is a bit unusual from previously overlooked, but still, it's something a bit different, just a bit different. All right. So let's maybe take a look on some another things. Here we have a so-called variable data. So please take a look on the definitions. So we have the warehouse, and at the warehouse, well, you can imagine that it's not the warehouse, but it's let's suppose a shop. So in the shop, in the beginning of the simulation, we have 700 items. So 700 products we have there, and daily customers buy from 40 to 63 items. And our task is to create a simulation in which once amount of items becomes less than 600 items, then the market or the shop makes the order of of, of delivery, and delivery takes 5 days. So after 5 days, there will be a delivery of 500 products. So um, so that's literally is the task. Okay, great. So literally, what do we have to do? So the first of all is a definition of the variable, which once we reach, we run the equation, and within the equations we can have the following writing form. So errand 1 at 24. So errand 1 means the random number, and we get one number. After the add, we specify until which number we are getting the randomized number. So it will be from a 0 till 23. So literally till that number we mentioned of -1. That means that every time we get access to var2 value, this equation is being recalculated. That means that the result will lie in ranges between 0 plus 40 till 23 plus 40. So, which means from 40 till 63. That will be the value which will receive access in this var2 variable. And when we would like to recalculate the value of the variable, we have to mention them as variable. And then when we do that, we have to get access to such variables using $v and $sign. In this case, we have right here the implementation is a bit incorrect, but let me show you the essence of this. So we have 20 days. So here by the generate, we generate another day. So we find out if we have enough of the products to fulfill the customer needs. And if we have enough, then we are selling those products. And as you can see by the terminate, we end the day. We have start 20, so it means that we have 20 days. And 20 days we have. So what happens in the parallel? In the parallel, we execute in one transact only once. So you see, I don't have the average time, I don't have the time dispersion. That means that the transact is being done only once. That's the first thing we have to try to keep in mind. Okay, what happens nextly? Nextly, we find out if in the stock. So $X, I'm reminding you, that means the numerical value of the stock is compared to the numerical value of the point. So if stock is less than point, so if left products is less than 600, then we're going to the next code line. Since here there is no the else case and there is no line to which we are sending the transact, then it means that if the equation is not correct, we are checking the equation again and again till the case when it will be correct. So once it's correct, in other words, once we have less than 600 items, then we wait 5 days, and after 5 days we add 500 items to the stock. And unconditionally, we go again for such check. And that happens in the loop all the time without any problems, and we receive, well, let's call it good results. And we receive always this delivery of items. Do we have any questions about this solution? Okay, um, no questions. All right, all right. Okay, so let me take a look. What is the next one? Oh, okay, the next one is a bit more complicated stuff. All right. Well, I don't know, guys. Maybe that will be frankly saying quite enough for the first time taking a look on the GPSS. Because we can make a deep dive in a lot of other things, but the question is, will it be fine to do that? Okay, so what would you say if that will be all from my side for today? Maybe you have some questions. Maybe you have some specific questions about these codes and about these examples I showed you. If you have, feel free to ask. So, what would you say? Okay, so the next week we will do tasks related to GPSS. So we will have a sort of uh, class tasks. You will be trying to make them, and we will try to find out how we can fix them. how it would be better to implement them, it will happen in that way. So to make the answer short, yes, we'll be working on this. Yeah, exactly, because it's quite a lot of new information for you. So you have to rethink. You have to think about this information. You have to maybe try something. Maybe try some codes. All right, guys. So then let's then finish for today. So thank you guys for being connected. I really appreciate this. So next time we will be working on all this and we will be continuing taking a look on another cool and interesting stuff related to GPSS. Alright guys, so see you next week and have a nice weekend. Bye bye guys.